So the title of this talk is Architecture for Real-Time Data. And I'm going to mix it up a little bit by talking about some non-real-time problems first. And just know that they are in the context of real-time, and we'll describe why by the second half. Quickly, I'm Theo Schlossnagel at Postweight on Twitter. I am the CEO of OmniTI. I founded a company called Message Systems, and I spend a lot of my time right now working on infrastructure challenges at a company called Circonus. I wrote some books. I speak a lot. I'm an engineer. I'm a member of the ACM. How many people here are in the ACM? Right on. How many people here are in the IEEE? Right on. Yeah, watch out for Brian Cantrell. He might pistol whip you when you're not looking. And I write a lot of open source code. So I look at a lot of other people's code. At the closing plenary today, I'm going to have a group therapy session that may only help me. That's a little insight. So what it is, what is it that we do here? At Circonus, we monitor stuff, right? And we monitor other people's stuff specifically. It's a SaaS offering, and it's lots of other people's stuff. And the goal of monitoring it is to take all that information and store it and allow you to trend it and provide analytics. And we also allow real-time, and when I say real-time, there's hard real-time systems, which I don't deal with. And then there's soft real-time systems, which you get to define any way you want. So in our environment, what it means is sub-second analysis. So if I have an event come into the system, within 1 second, typically within like 100 milliseconds or 50 milliseconds, need to take some sort of action on that event. I need to alert somebody. I need to send a message to your pager that says something's broken. So how do you do that, right? So this is our architecture, awesomely oversimplified, right? And I'm only going to talk about two pieces. And first, I'm going to talk about the storage component of that. I think there were some really interesting engineering challenges is why, and we did it a way that worked, that we ended up, I consider, not the right approach. But it made sense, and maybe it made sense. Well, we can all be the judge of that. So what happens when data arrives, right? We have to store it. We store all the data that arrives for graphing, for visualization. Some people here like track data and put it in an RRD tool or something. All right, yeah, so you've seen a graph before, right? Like bandwidth graph, CPU utilization graph, all that kind of stuff. How many people here do statistical analysis on their data? Like have a graph that shows standard deviations and error bars and margins, and that's a surprising number of hands. That tends to not be done in systems because people are using RRD tool and it has no features. We also need to export the data, and we need to be able to query it in real time. So this is where the storage system starts to touch on real time. So I have all this data that comes in, and I need to put it into a database, and I need to get it in there, and that's fine. But now I have the data coming in, and within 100 milliseconds, I need to make a decision on new data coming in. So what happens when my decision on that data requires context from last year or last month or last week, and it's in that storage system? I now need to be able to query that data in a very strict soft real-time sense. Like I need an answer in a millisecond or 2 milliseconds. So the data comes into the agent. This is how this works. We use an open source product called Reconnoiter under the hood, and this is basically how Reconnoiter works. The agent runs a check. It's like a Postgres check, and it does a query, and it times it and gets some data back. And that check has a UUID. And it'll have a whole bunch of metrics that come with it, like duration or row count or something like that. Or I'm doing a ping check, and it'll do the turnaround time, the number of packets that were sent, the number of packets that were received, the minimum, the maximum RTT. Those are all metrics. So we get all this data that comes in, and it's unique by UUID and name. So what we do is pretty straightforward. It's out of the rule book of scalable systems. I have a limited number of these check metric combinations, right? So how many do I have? 1 million, 1 billion? Okay, those are all small numbers in the world of things. So let's say I have 1 billion. Putting 1 billion rows in a table is not something that's hard. So if I'm just going to put 1 billion rows in a table, that's not so bad. And if those rows only say this metric lives in that database. So it's a mapping table, right? It's one table that says this metric that you're looking for, that you need to store right now, it lives in what we call them SDBs, this SDB 12, SDB 3, SDB 2. So we look it up, and then we go insert the data. And now, of course, the billions of metrics or millions of metrics have hundreds of millions or billions of rows behind them on those tables, and those scale out. So I can just add more. So it's basically a lookup table. And so I insert all the data. Data comes in, I figure out where it goes, stick it in there. And then on each of those nodes, it's a map problem, a map and reduce pretty much. So I ask them all to do materialized views. So every 5 minutes, it goes look at the data, and it rolls up and determines things like the average number, the average value, how many data points there were, the standard deviation. It takes a derivative over time and stores that. So it stores these aggregates, and that way, when I go to a graph and say, what did traffic look like today? It goes into it says, oh, that's stored in, that octets on that switch port. That's UID foo octets. It says, okay, that's on SDB3. SDB3, give me the 5-minute intervals from midnight to midnight. And then it spits back 144 values, or 288 values, however many 5 minutes are in a day. So it's pretty straightforward. And that works pretty well. In fact, it scales pretty well, too. And SQL certainly has its perks. So one might say, like, I just have data here, right? Like, why am I using the overhead of SQL? And it turns out that when bad data comes in, you can actually go back in, and with these nice things called queries that you can just easily articulate, you can go and munge the data and fix the data, and you can fix it up and then rematerialize the views and stuff like that. If you have a question that you want to answer that you didn't think about when you were designing your data model, you have a very, very robust language, query language, to ask those questions. So you can ask really unplanned queries or new ad hoc queries. And then life changes and you need to store different data. It's really easy to add new data type, right? I add a new table, new data representation. I mean, there's syntax for this. It's really, really simple. But SQL certainly comes with baggage, right? I mean, it's a very high overhead protocol and query language for doing like sub 1 millisecond queries all the time. I'm asking a question of give me the 288 5-minute windows over this thing. Like, I don't need to figure out what table that's in. I don't know the where clause and all this stuff. It has to parse all of that. And it's usually kind of chatty. Really, I just want to, ideally, I want to send like a UDP packet and get a UDP answer. But if I'm lazy, I'll send a TCP connection where I connect, send one packet and get one packet back, and I'd be done, because that's what I really want. Sharding is not magic. This is data sharding or federation. It's actually a very traumatic experience. So when I put everything on SDB3, what happens when SDB3 crashes? Okay, well, there's that problem. Okay, so what I'm going to do is I'm going to take SDB3, and SDB3B is the backup of that. So now I have streaming replication back and forth between those two. So that's basically the way our architecture worked when we started. We had 4 of these nodes, SDB1 through 4, and then we had 4 nodes that they replicated to. So we had this, and this is really common. How many people run web architectures where they've got shards and each one's got a master-slave or a master-master or something like that? It's a really common pattern. If you ever worked at Yahoo or Flickr, you have to do it that way. Apparently, it's baked in. You have like a tattoo right here that says you have to do that. So it's not a bad design pattern, right? The problem is that we have problems with it. The performance is really suboptimal. I can't get reliable systems performance. The storage consumption was actually the leading reason why we had to come back to this, and we got a little set of crayons and a napkin and decided, can we do better? And really, it did not happen on crayons and napkins. It happened with a pen and a piece of paper. But I think that's where most of these problems really need to start. So if you look at the system that we were doing, at least, we have these data streams, right? I'm asking for data like octets on a switch, out octets. I get a number. I get an unsigned 64-bit int back every time I ask, right? And I have a stream of this data coming in because I'm asking all the time so I can draw these graphs. So for just 10,000 of these streams, that ends up being 5.25 billion data points per year just for 10,000 streams. I mean, 10,000 streams, not that many streams. That ends up being a lot of space. It ends up being 500 gigs of space in a relational database, right, for just 10,000 metrics. 10,000 metrics is half a terabyte for a year's worth of data. And the reason is because you've got these UUIDs. You'd have to normalize all the data to get it a little bit lower than that, but then you have to do all these joins against multi-million row tables. And that all works. It just doesn't scale it's not very performant. So there's a difference between scalability and performance. The solution that we had come up with, I can do 1,000 SDB nodes, and it'll just work. But then I'm left with 1,000 nodes. And my thought in that process was, like, this just doesn't feel right. I should be able to do more with a given piece of hardware. And we also kept running out of memory. The roll-up jobs and things like that, honestly, I could have just made that the database team's problem, and they would have worked through it eventually. But that was an annoyance. Loading the data was somewhat expensive, and this is due to the fact that SQL gives you a lot of promises. And I actually don't really give a crap about a lot of the promises, but it has to make them because it's making them to someone else at the same time. And more importantly, SQL is making a promise to me so that it doesn't break a promise to somebody else. The view consistency aspect of that and the isolation aspect of that. So it has to do a whole bunch of work to isolate me from someone else so that it doesn't lie to them. And I don't care about that either. Like, there's all this baggage that came with ACID databases that I didn't really care about. And querying the data was too slow. And while we had these failover nodes, right, the nodes popped way too frequently. It's not like Amazon where it just disappeared, but I mean, it was like at least once every other month we had a node pop. And our fault was we made a mistake that we didn't build the client APIs that access this data in a seamlessly failover way, right? So if the node popped, the client went like, fuck. And then a DBA logged in and promoted the slave to master, and it took 5 minutes, and they did that by hand. And that wasn't even the annoying part most of the time, right? The annoying part was that then the DBA was like, fuck. I have the master that's no longer the master. I'm going to destroy it, re-image it off the slave, and rebuild it, right? And you say, well, like in MySQL, that's one command. In Postgres, because automation is powerful, it's also one command. Right? It's a lot of commands get run in a script, but it induces a tremendous amount of traffic on the boxes, right? It saturates the I/O well. It's reading all of that data over. I'm copying 250 gigs of data over to another box. It's a lot of work that, like, hey, guess what? You're supposed to be serving real-time queries, and you're actually doing, like, basically a backup at this point. And we weren't leveraging any of the relational features. So immediately, what did we do? We looked at NoSQL solutions, right? I looked at Hadoop HDFS, mainly because a lot of the data we get coming in is tab-separated format. It's awesome. I designed that. I'm very, very sorry for it, but that's what happened. If I could do it again, I'd probably do protobufs. In fact, one of our tab-separated formats, the fifth field, is a protobuf that is gzipped and UU encoded. And actually, that works amazingly well. So had Hive been there when I started doing this investigation, I think it probably would have made it all the way to the prototype I regret running in production phase. But we looked at HDFS, we looked at Cassandra, we looked at React, we looked at MongoDB. All of these things failed because they didn't meet the trifecta of needs that we had, which was data storage, specifically data storage. Most of them failed on that. The data safety aspect of it, like, I can relax a lot of the relational constraints and ACID constraints, but like, the data needs to fucking be there when I come back. And then the IOPS problem. So a lot of them sacrificed one of these to get to reduce IOPS on our systems. And what I needed is to reduce IOPS on the systems and not sacrifice. So I did a lot of work in the Hopkins Center for Distributed Systems. So I'm familiar with read all the papers that powered these things. And the inspiration here was someone implemented a paper that I liked a lot, and they did it differently. So I was inspired by that. But React had this bad data storage space problem for my problem. Like, they're solving a problem, and I have a much more refined, understood problem than they have. So the first thing you always say is like, do I build it myself? And of course, all of us who are engineers were like, yeah, I can do this. This is awesome, right? I can build it myself. I can build it better. I can build it stronger. 2 months from now, you're like, guess what else I need to build? But I can't because I'm maintaining the thing that I just built, right? So you have to make really, really conscientious decisions on what you decide to build. So the first thing is, why in the hell would we think we could do a better job of this? And it's not just because we have 2 people in our company, one of them who managed to get their PhD, and the other one is me, that understand distributed systems very, very well, right? They've written papers on distributed systems and distributed crypto and distributed transactions and databases and things like that. It's not a reason to write software. The reason that we did it is because our data is different. We only ever do commutative operations on our data. And whenever you talk, if you ever mention that to like React guys or Cassandra guys, they're like, well, that problem's easy. Like, yes. Yes, it is. And I don't have to implement all that crap that you implement and get wrong sometimes. So I'm not worried about fucking up the hard stuff because my problem is limited to the easy portion of this. A commutative operation is one that the order doesn't matter. The outcome is the same regardless on the order. So if I roll up one 5-minute window and then roll up the second 5-minute window and store them in the database, and another database gets them in different orders, the standard deviation, when you roll them together again, it can be the same. It doesn't matter. All of these things, the order doesn't matter. As long as all the data gets there eventually, I don't have to worry about ordering constraints, which means that if I have a distributed system that splits apart and some of it gets there, I can stream them back together again, and I just don't care. All I care is that the data eventually gets there, which is really, really cool. So we did some back-of-the-envelope math, which we'll get to in a moment, and basically it was like, if we can hit these numbers, this is so worth it. So at Circonus, we name everything after Muppets. So enter the Snoth. Anybody know what the Snoth is? 2. Oh. Anybody know Phenomena? Right? The backup singers. They're the Snoth. All right. Do, 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 do. So it's written in C, as God intended. Right? This works. All right? The reason that you write things in C, we'll get to also in a moment. What it does is it stores aggregated rollups. We get to choose what our rollups are. So in the system that we have now, we have 5-minute rollups where we store data in the system in 5-minute increments. And we store data like how many data points compose this unit, what's the derivative, what's the standard deviation on the average, what's the average, all of this stuff. We store like the statistical aggregate information for 5 minutes. And we also roll it, and we amortize this roll-up into 20-minute, 60-minute, and 1-day roll-ups. So when I insert a 5-minute window, it says, oh, I dirtied that 20-minute window, and it rewinds out, and then it takes those 5 minutes, and then it rolls it up into the 20-minute and stores the 20-minute, and then it rewinds out and says, I'm going to update the 60-minute, and then it winds out and updates the day. So anytime I go to ask for data, I say, hey, I want data from January 1st, 2008 to January 1st, 2010, and I need 1,000 data points. It's really easy to do the math and say, how many pixels do you have, right? Well, I'm not going to give you 5-minute increments. What I'm going to do is I'm going to give you day increments because that's actually 600, it's 700 data points basically. You only got 700 pixels on your screen. I'm just going to give you 700 data points. Oh, you need standard deviation in there? I'll give you the standard deviation of all that data. That's fine. I have that. So all of that data is there. It's really fast. And the beauty of that is that that's 600 data points. If you think about that, how many disk blocks does that take to store 600 data points if you store it well and you store it temporally local to each other? So we store one file contains one of these like 20-minute streams or 5-minute streams, and we store those. And because they're all aligned, this is where it gets like indexes. Fuck you, indexes. I don't need indexes, right? I know that the epoch is, say, January 1st, 2008, right? So I have a 5-minute window in the future. I can use a file offset. I have a discrete number of them, and they're actually quite small. So I can use a file offset, and now I don't need indexes. Like, I need my birthday. I need January 11th, right? So I'm like, how many 5-minute offsets is that? I'll advance that meaning number of fixed record lengths, and I'm done. Really, really simple. So now, kind of the beauty comes in the data storage format. So what we did is we used something inspired by Dynamo. It's a consistent hashing algorithm. Basically, we have nodes pop up, and they take some fraction. So each node pops up and has, in our system, a configurable number of virtual names. Each node has a UUID, and cleverly, UUID-1, -2, -3, -4, -5 are their virtual names. So a node will boot up and say, hey, I have 64 virtual nodes. So I'm UUID 1 through 64. your UID 1 through 64. If you're a bigger system, have more IOPS, maybe 1 through 128. So all of ththese virtual names, we take a SHA-1 of them, and they put them, that's 256 bits of distribution, and we map them. So now I have all these points on this ring, this 256 SHA ring, and each of the virtual nodes lives on it. So now when I have a UUID, I don't need to go look in a table. I take the UUID metric name, and I hash it with a SHA-1, and I put it on that ring. And then I say, who's clockwise from me? You're on that node. Right? And then, in a clever way, we actually go 180 degrees. We go pi radian around. And then we go clockwise and find somebody else. And the reason we do that is very clever in that if we want to hack the system and make sure that one data center always hashes to one side of a ring and another data center always hashes to the other side of the ring, we can actually have seamless, guaranteed cross-data center storage for the stuff. So that's a hack on top of Dynamo that we added in. So that's actually really not that hard to write. The hard part of it is getting it right. And the beauty of hashing and doing all of this stuff is that, you know what? If you get it wrong, you're still right. It's the second implementation has to be equally wrong. It has to be wrong in all the same ways because your second client implementation that's like, hey, where's that metric? It's like, it's over there. It's like, fuck. All right, so we have a bug in the way we were doing that on this system. Let's re-implement that bug because I have billions of data points stored. And I have a bit error, flipping the bit. So this is awesome because Theo can't do binary math. Like I said, half of the ring is split, right? So what do you use? You use the most significant bit in your 256-bit system, right? Bit 1 tells you you're on the left side of the ring. Bit 2 tells you, if it's a 0, you're on the left, and it's 1 on the right. I didn't use bit 1 by accident. I used the wrong hex symbol in there. I used bit 6 to 8, and a bit 8 in a 16-byte word. It's like 8 bits in. That one is the left-right. It's like, fuck me, right? So that bug exists all through the whole system. It's not a bug, it's a feature. We put it there on purpose. Doesn't change the dynamics of the system at all. So, and then what we did, because not everybody writes in C, and a lot of this stuff we're getting creative with, one of the things that we like are like stored procedures. So we embedded Lua in the system to allow you to iterate over data in a scripting language that really is brilliantly embedded in C. And then we can actually serve complicated data. And this is how we do things like, give me a Holtz winter prediction window over the last 2 weeks. I say 2 weeks, and it like kicks into a Lua scripted mode, and then it goes and reads the data, does all the statistical roll-ups and aggregations, and does that, and does predictive analysis, and hands me back data that didn't exist, that it made up. Trivia, Snoth has no plural, so it's a sauna of Snoth is the cluster. And that's trivia that is too erotic for this conference, by the way. So next time your children watch Phenomena, know that there is something sorted behind it. It's disturbing. So the on-disk trick. So we have a columnar database, basically. We have these files where we're just storing data as it comes in, right? It's a columnar database. The beauty of this is that the metric name UID is stored once, right? It's the file name. This is really easy. I don't have to store that data over and over again. The timestamp, I store an epoch in the header. Like, this file started on this 5-minute window. So now if I want data in the past, it's really cheap. I look at the header and go, no. If I want data in the far future, I look at the header and check the file size and go, no. And if it's inside, I just seek to the offset and give you back the bytes. But what that means is we're only storing data in the file. And one of the things that we notice in our year's worth of data that we collected over a whole bunch of organizations is that, you know what the most common data point is? Anybody can guess? 0. There are a ton of zeros, right? And if you have a timestamp in every one of them that's different, that does not compress very well. So what we did by getting only the data in there is that we were able to do tricks on disk to make sure that the same data point coming in over and over again, whether it's 0 or, hey, your link speed is 1,000. Yeah, it's still 1,000. It's really 1,000. And what's awesome is when you unplug it, it's like, no, it's still 1,000. It's just off. Like, you actually have the same number. It should be like hard-coded in lettering on the switchboard. There's no reason for monitoring it. But people look at it. And by highly compressible data, we reduce the number of IOPS dramatically. I'm writing one disk block. That's it. So when you get into that, it gets a little ugly. Talk about bit squeezing. I feel like I'm on like an ELIAC machine where it's like, it's just another bit. Just give me another bit. Just one more, and I can do this. So you ever heard of 16-bit IEEE floating points, anybody? Yeah. Don't do that. We actually opted against that. We need that, so we have a hack that's in there that's different, where it's like, I have a 16-bit unsigned short, and then we came in to this problem where we needed to store slightly more data than we thought, and we're like, I need something more than 16 bits. It's like, give me one more bit. One more bit over here means that's not a 16-bit UN. It's something else. So we code in a mantissa in there, and we kind of hacked it ourselves because there's no good IEEE 16-bit floating point, and nobody claimed that Python has a good one because it's not. So we used a year of data, and we were able to take this structure and compress down the parts and choose a double here and a float there and a 16-bit value here to make sure that our data could adequately be represented. And we juggled them around and wrote all the data out. And then we changed them around a little bit more, wrote all the data out. We reordered the structures in there so that LZO on ZFS had a field day with it. And did this pay off? So we dropped 500 gigs for a data set to 13. And that's 97%. It's a 97% reduction in our internal cost for storage for storing everything that we store. So was it worth it? I would say it's absolutely worth it. The IOPS are, I don't have 97% less IOPS, so I won't lie about that. But you have a tremendous less IOPS, right? Because there's a lot less data on the disk. There's more that fits in the ARC. I need smaller machines. Everything is much better. Of course, I don't get smaller machines. I just put more data on the same machine. Because of the way this works, there is no name node. There's nothing. We have nodes. I just take a node offline, bring it up, run it in debugging mode. I can, like, if you don't answer, somebody just go to the next one, right? So we have nodes that we can just drop in production and upgrade, reinstall, do that. No interruption of service at all. Not a single request lost, and it wasn't difficult to implement. So there's no single point of failure. And this is the real reason why that you write this shit in C and you write it correctly, is that this has been running, so I ran this, I think, yesterday or the day before on our box. It's been running since June 28th, was the last time I upgraded. It has 78 megs of resonance set size. And this manages every fucking data point on this box, right? It's nice. 0.01% CPU utilization. So it's not all peaches, right? So we have 8 weeks of time to build the solution over about 3 months. So I had to lock myself in a room and go write C code, which I did. I'm not putting it on GitHub later, but it was very enjoyable. And then we had to maintain it. So over the last 8 months, it's taken about 4 weeks of engineering time to do maintenance on this. Particularly, we also store text data in this system as well. So if somebody like has a SSH fingerprint, they get like the hex. We store that hex code. HTTP codes are actually text. We store that. We use BerkeleyDB as a backend, and I still am walking different from that experience. So we're actually switching that to Google Level DB, which is good. It's been a decent experience so far. It's C++, so it's actually dirty and miserable because I like compile it and deploy it and it crashes, and it's like, oh, different C++ ABI, like different compiler. And the problem is now we need to store a new data type in there, and it's like, wow, you know what? Create table seems like this distant fond memory right now. I would love to do that, but it was a huge win for that. And as our lead engineer Clapper said, every time he logs in, it's always reminded that occasionally I can write a piece of software that works, because all the rest of the time he's spent debugging the other crap that I shouldn't have written. So next, what does this end up powering? The real-time component of our system. So we collect real-time data. It's a pretty simple concept, right? We're collecting all this data, and it's all point A. There's a lot of point A's out there, and they're all trickling data, and it's going into point B. And point B needs to do streaming analytics on it. I need to be able to say, I'm checking these octets on this switch, and if the derivative of that number over the last 5 minutes exceeds 129738, I need to escalate to severity 2 to that guy, right? So kind of complicated. Luckily, there's great systems for this. And then the outputs of that are multiple. So it's pretty easy. It's a lot of data into a point and then out again. So we use Amqp for this, specifically RabbitMQ. We've had really bad pathological failures that I would say that are kind of our fault. The Amqp specification is really, really complicated, and once you understand it, you will understand very clearly that everyone who uses it incorrectly. So for example, like durable messaging, right? You would imagine, right? We all know what D in ACID means, right? So when you send a message, and the guy in the broker there says, I got it, right? Awesome. And then the broker crashes and comes back up. He's supposed to have your message, right? No. That's not what durable means in Amqp. Durable means that the queue that had it is there, not the message. The message would be persistent, not durable. It's like, fuck me. Like, how? Like, you have to redefine every fucking term that I know in your specification something different. So it's very difficult to get your head around what you're actually doing when you use the protocol. The failover technology in RabbitMQ, which is supposed to be better in 2.6.1, which we haven't upgraded to, means that if you have a durable queue on one box and it's in a cluster and it crashes and you're like, oh, I'll use the other guy. It's like, no. There's a durable queue on the other box. And I'm like, that box is gone and you're in a cluster. And it's like, yeah, but it might not be gone. It could be there. So I can't give it to you. And it's like, what? So we actually ended up not clustering any of that stuff and doing it ourselves. And I don't know if we'll flip back that works. So the great thing about Amqp, though, is that there are a lot of libraries for client languages that are implemented fairly well. There's a Ruby gem that's there, which we don't use Ruby. Our stuff works. And we do a lot in C. There's a C library from the Rabbit guys, librabbitmqc. There's a Perl one, which I maintain, and the Node.js one, which I now maintain. And then there's the Java one, which is actually an excellent library, and it's done by the Rabbit guys. And just to be clear, when this gets annoying, we use HTTP, right? We'll just like batch up a payload for 10 milliseconds and put it at a URL. It's like, that's messaging for you. Because I got a 200 back, and I know what that means. So streaming analysis, there's a lot of stuff here, right? People have been doing this for a long time, and they're very good at it. Think the stock exchange. Anytime you look at a high-frequency trader, right, I mean, they're doing this. They're looking at the current market conditions and trying to make an educated guess. And they spend a lot of money trying to do this well. So there are some products, which I will classify into the legacy category. Some of them are very new, too. SQL Stream's pretty new. Treviso, Drools, OpenESB, Esper. And then there's some new solutions which are more distributed in the map and reduce model, like S4, Storm from Twitter, S4 is from Yahoo, Storm's from Twitter, and Hop is an implementation of an academic paper. It's called the Hadoop Online Prototype. We use this. So, all right. So the interesting part here is we're back in the exact same situation, right? Scale up, scale out. How do I do this, right? Do I want this magical distributed system a la Snoth that we were successful with? Or do we want to try to scale this vertically and use something else, right? These S4 Storm, they're just freaking magical, right? Just add more nodes, does more stuff. We had some learnings, and we had a different perspective on this. And I hope that the one thing you get out of this talk is that, like, just because you implemented something in one time doesn't mean it's going to happen the second time. Right? You need to look at the situation and figure out the problem and really decide from a business point of view, is this investment worth it? It's going to be worth it in the short term and the long run. Debuggability in these systems is paramount. And streaming queries can be extremely complicated. They're hard enough to understand. They're even harder to debug. And at least given my experience, debugging in a distributed system is like playing Russian roulette. So I understand Dynamo and commutative transactions enough that I don't need timing sequences. I don't need Lamport time stumpers. I don't need vector clocks. Like, those problems evaporated when we implemented Snoth, which is why we chose to do it, because it was easy enough that I don't need a team of distributed systems experts to manage it or debug it. If we built this ourselves, I thought we would need a team of people to do it. There are a lot of new solutions that are coming out. I'm not sure they have a team doing it. So when there is a bug, how do I know it works right? How do I trust these solutions? The people who put money through their system and make money on the other side, so everyone who uses the technology on the stock market, if they're using it today and they used it last year and they're still in business today, right? I trust it a lot more, because if it didn't work, they would not be in business. The old systems, because they do financial trading, are high performance. So they do like 350,000 queries per second on a commodity box, 350,000 data points a second. So you're running all these streaming queries, and you can stream hundreds of thousands of events per second, and it's just like, oh, that one. Hey, that one. That works. We see less than that because our queries are a little bit more complicated. But the beauty of this is that we run a SaaS model, and one client can't see the other client's data anyway. I don't need these in a single system, right? I can federate this problem. I can take one account and put it on one Esper instance, and I can take 5 accounts and put it on one Esper instance, but I don't need one account on 10 Esper instances, because at least today, we don't have a single client that can break it. We don't have a single client that sends us enough events that we can saturate a single powerful node. I don't think we will for quite a while. I mean, how many people here actually pull in 350,000 metrics per second for their architecture? That's a lot of metrics per second. I mean, if you're monitoring 350,000 things and you're doing it every 30 seconds, you'd need a 30 times larger architecture to do that. I mean, that's a lot. And you know, if you come, we will build it. It's a little Yoda-ish, but we'll fix this problem if you have more than that. So you don't have to horizontally scale everything. I mean, you have to horizontally scale everything. You don't have to magic scale everything. Not everything needs to be magical, add a node, redistribute everything, right? Federation is a really legitimate approach to some problems, especially when debuggability and observability are important. The last thing I want to do is to have an event from an important client come in, scatter to a cluster through some sort of map and reduce streaming analysis, and be like, yeah, it didn't alert on the other side. I'm like, fuck me. Right? The problem is all these events are streaming in, and it's the context of the situation that sets up the environment. Like the bug could be induced by some other metric somewhere else in the system. These things are really difficult to debug, and I like them to be contained on a single box. Like I would love this to actually be on a single processor, not even threaded, because then I can have causality inside the state machine that runs in Esper, and I could debug it if I needed to. We saved huge on the long tail storage. And we kept the stuff in the real-time federated to keep it simple to operate. And if you do write anything in C, which I highly encourage because it's a cleansing experience, you should look at Lua. Embedding Lua, the World of Warcraft guys got it right. So when they chose to embed that, it radically changes how you can do instrumentation in your application. You can ship, message systems guys have shipped hot fixes to their app in Lua because they have FFI bindings, right? I mean, like crazy stuff that you can do by just exposing the right parts of your C in Lua, and you can load a script in that instruments all these hooks in your system and finds symbols and ties them together and rewrites stuff, and you can do all of that stuff without recompiling something, and you can test it in production. If you're testing and you're not in production, get the fuck out. Right? So nobody interrupted me at all, but does anybody have any questions? I didn't show you how to build anything, but hopefully gave you ideas. So the question is the offset style that we hold our data in. We use time series data and we have offsets, and we're seeking around in that. How does that affect the compression algorithms? So I was actually really concerned about that. The way that works is that there's a record size in ZFS, and it always has to write the record size. So if you're going to go seek somewhere, it's going to load that record and then write it and compress it. And occasionally you'll overflow out of that. So there are very rare circumstances, rare enough that they equal 0 in production right now, where we will actually take a lock on the file, copy it to the side, and restream it sequentially in, just to make sure that it recompresses well. But the beauty is we tend to get in all of our data in order per data file. It comes causally in order. It's very unlikely that I could ever receive that data out of order. It works if I do, but it might cause that sort of fragmentation if I seek forward and write and then seek back and finish writing here. That actually happens, once in a million or once in 10 million writes. And it doesn't hurt anything. Anything else? Nothing else? Well, that's it? Yeah. Oh, yeah. So the way we do it, we use a product called JLog, which is open source, powers a whole bunch of other stuff. Every node keeps a durable on-disk queue to every peer. So when you write, it does a hinted handoff. It doesn't do hinted handoff. It's backwards from that, but it does. It's like a write through. So when the client writes, it can write to one node and then it streams to the second node, right? And it'll choose it. So all of those are durable queues, and when the node's down, you can see all the other guys in the cluster like, dude, you there yet? You there yet? You there yet? And when it comes up, it just, they all attack it. And what happens is when the node comes up, it will set itself, the way the ring works is we have a configuration that describes all the virtual nodes in the system, and we order it and take an MD5 hash of that, SHA hash. We love SHA hashes, I don't know why. Hope they accelerate that. And we have a topology and a next topology. So if I change the ring, we recompile it, redistribute it everywhere, and everybody says, hey, my next topology is this. And they all do their work to redistribute stuff to go to the next topology, so if we add a node. And everybody works to that, and then when they've graduated and evacuated all the data that needs to be gone and collected all the data that they need to have, then they graduate to that ring and the other ring goes away. When a node initially boots, it has no active ring. It has a future ring that it's converging on. And as soon as all of the clients send it all the data and go, we're up to date, then that ring just pops up and it can answer queries again. No. Every node, each node, so each destination node, because we just stream them over the same channel. We tried to use ZeroMQ, and I feel incredibly burned because it wasn't stable when we tried it. It was so long ago. It was 18 months ago or something like that when we first, I guess, 9 months ago, but it wasn't stable at that point. Seems like if I was to do it again, I would probably have done that streaming part across nodes in ZeroMQ. All right. Thank you very much.